Hello everyone, welcome to this course on performance evaluation. We will start with a few organization matters. We're using Zoom. Don't hesitate to use the chat to post your questions. I am Jean-Yves Le Boudec. I will be giving you this lecture, and I am assisted by Ehsan Mohammadpour, who is here in the room today, and Hossein Tabatabai, who is also here in the room and is the Zoom master for this session. As usual, every documentation relative to the course is to be found on Moodle. So this course is about performance evaluation, which is using the practice of statistics, probability, and modeling to whatever project in computer science or communication systems you are doing. So it has both a theory and a practice part. We are in the lecture today, so every Tuesday we'll have a two-session lectures, so twice 45 minutes, followed by an online quiz session. And on Wednesday, we'll have another hour of lecture followed by labs. The online quizzes are meant to foster your learning experience and make sure you learn the theory as we progress through the course. So every week, I post on Moodle one quiz with a number of questions that you can answer directly into Moodle. Then you can test your understanding. You can submit the quiz, and you have to succeed it with at least 70% of success rate. But the grade does not count. So the idea is really for your own learning experience. It's not for evaluating. It's not for evaluation. It's only for progress. You can do as many attempts as you wish. So the idea is that if you fail at one of the first attempts, then you have a look at the hints that are given, and then you can try again. You can try as many times as you want. The grade does not count, but you must be up to date to upload your homework. So every week there is a quiz. You should, depending on your background, it's between 20 minutes to 1 hour and a half to do, depending also on the nature of the quiz. This week's quiz is perhaps a bit shorter than other ones. Some will have a bit of theory. You may need to do a bit of maths to answer the questions. But it's roughly speaking order of 1 hour of work. I strongly encourage you to do them every week. The grade does not count, as I said, but the quizzes are chained. So in order to do quiz number 2, you must have gone through quiz number 1, etc. And in order to upload homework number 1, which is at the end of the second week, you must have done the first 2 quizzes. The quizzes are also a preparation to the final exam. That will be questions of similar nature as the quiz, except the exam will not often be multiple choice questions, but similar in nature. Another important part of the course is the practice. It's in the form of homeworks and a mini project. There are 4 homeworks of 2 weeks each. So during the first 8 weeks of the course, there are 2 homeworks per week, which are programming assignments about one aspect of the course. The first homework that starts this week is about the scientific method, how to use results of numerical evaluations in a scientific way. We'll talk more about that later today in the lecture on methodology. Then towards the end of the course, we'll move on to the mini project, and I will mention that in more details in a few more slides. Those 3 aspects of the course, the labs, the final exam, and the mini project have equal weight. So if you want, the theory is 1/3 in weight, and the practice is 2/3. The exam details will be fixed when we know exactly what happens with the sanitary situation. We probably will do a take-home written exam to be done via Zoom, but the details will follow later. I'm giving slides, which in principle are sufficient for most of what we do. The slides are based on a textbook, which is given here. So this textbook is freely available and in PDF on the website that I'm giving here. So I encourage you to download a copy of the book. So if you're interested in more details and in particular proofs of some of the results, they are all given in the book. This is an outline of the theory. We have 9 chapters. Today we'll start with methodology and we'll continue next week with confidence intervals. So those are, as you can see, topics that are really to do with using quantitative analysis in a sound and scientific way. The other chapters we'll discuss in due time. Each of the different chapters, for at least the first half of the chapters, will correspond to a homework, lab 1 to lab 4, that we will discuss in due time in more detail. I mentioned the mini project. So the idea is that towards the end of the course, something that is the size of the last 2 homeworks, so for 4 weeks of work, I propose to you to apply what you will have learned in the course to your own project. Because the idea of performance evaluation is that for most people, you do not become an expert in performance evaluation, but you need to evaluate the performance of some research or development project. So the assumption that I'm making is that most of you have done in the past or are doing now a project, a semester project, or it can be some project work in some other course that is happening in parallel or that happened in the past semesters. And you can use this course now as an opportunity to solve a performance evaluation study for the project that we did. Most of the time in projects, we evaluate the performance, but perhaps we don't devote enough time and do not have the methodology to do it as well as we would like to do it. So the idea here is to give you this opportunity. So I expect all of you to have a very different project from all projects will be very different. Here are some examples of past projects. As you can see, they have to do with things like performance of a compiler, performance of garbage collector, but also some data science topics like evaluating fairness in classification, etc. I'm giving in the slides a subset of the projects that were done in the past editions of this course. This is just to give you an idea that feel free, whatever topic you are doing should be a good vehicle for doing a project. If you're really stuck, if you have absolutely no project, talk to us, we'll find a solution. But again, the idea is to really motivate you to think about what your project would be. The mini project will require you to do some thinking ahead of time. As I said, it's performed during the last 4 weeks of the course, during the lab time of the last 4 weeks of the course. But in order to make sure that everything is in good conditions, I require that you post a 1-paragraph project definition on Moodle very early, by mid-April. So on Moodle, you will find exactly the link for posting things. So the idea is you start thinking once you have an idea what you would like to do, and you write in 1 paragraph what idea you have. And then I will validate this to see whether all conditions are okay, whether it is something that is really doable in 4 weeks or not. We'll talk more about the details, but I really encourage you to already think about what this project should be. The goal of this mini project is to do the evaluation of something that you have done. So the goal of the mini project is not to continue a project. For example, if you're working on a database management system, continuing to develop the database management system is not the goal of this mini project. But if you have a database management system and an environment where you can run it and measure something, either in a simulator or in a testbed deployment, then that's perfect condition. So in general, the condition is to have some project which is able to produce some data that you can use for measurements, but the development of the project itself should be done already. Voila, that's for the introduction. If you have any questions, feel free to post them now or a bit later. One of the questions that I see on the chat is, what is the required knowledge for this course? Well, the required knowledge is a basic course on probability. So you should know what a random variable is, what a probability distribution is. You don't need to be an expert in probability, but you should have a first course in probability, like everyone in principle has in the bachelor at EPFL or equivalent schools. Of course, you should also be able to program, because the programming lab, the projects are essentially programming, require programming. The programming environment is either Python or MATLAB. The projects have been developed in MATLAB, but you're free to use Python, or if you use another environment that is okay for statistics, like Julia or R, that's also perfectly right. Good, then without further ado, we move on to the first technical chapter about methodology. So methodology is an easy chapter, as you will see. We will become more mathematical and more technical in the rest of the course, but it's perhaps the most important one. It's important for what we do here, but perhaps also for other fields of science and technology in general. So the first question is what performance evaluation is about, so that you have to know whether you continue with this course or not. And then we'll dive into recurrent patterns that we find in the performance evaluation activity, which are factors, how to use quantitative things in the right way, and a number of more generic patterns. Here's an example. Some people have done in the past mini projects, and papers have published a comparison of Windows versus Linux. So this is a very frequent topic for forums. Or a more technical oriented one is evaluate the power consumption of a telecom box. That's a hot topic in the telecom and in the IT sector in general, to make sure that the IT infrastructure is energy proportional. How do you tackle such problems? What do you need to be careful about, right? So those are one of the very first questions that come. Here's an answer given by one paper that I cite here in the lecture notes. So those people, Chen and his co-authors, compares Windows versus Linux. They use as metric number of CPU cycles, number of instructions, number of data read-write operations required by a typical job. And the typical job was done by loads that was generated by various benchmarks. So that's what you can read as a summary of this performance evaluation study. Another performance evaluation study resulted in the electrical power consumed by a telecom box is given by a formula of this type. The total power consumption is a factor times the max power consumption, which is the power that this box consumes when it is used at full capacity, P50, which is when it's submitted to a load equal to 50% of its capacity, and another factor times P sleep, which is the power consumes when it is idle here. So this is the result of a performance evaluation study. What is different about those things is that, well, what is common in those two aspects is we see that the first steps seems completely obvious, but doesn't hurt to repeat it. The first step is to define a metric. You want to evaluate the performance. Qualitatively, we would like to say it's good or it's not good, but in order to make sense of this, you will need to define what a metric is. And the metric has to do with the knowledge of the system you're evaluating. So the first thing you will realize is that in this course, we will not see a checklist of metrics and saying, yeah, this is what we measure and do that. No. Performance evaluation has to do with the system that you're developing. So you need to know your system, to know what makes sense. So the only question to ask is what makes sense relative to the goal of your system. For example, if you're designing, if you're working at Google and you're working on the optimization of data center, then the response time seen by queries coming to the Google search engine, for example, this is one metric of interest. If you're working on energy proportionality in IT infrastructure, then you might be interested in the power consumption. That's another metric. Now, the two metrics don't exclude each other. Probably if you reduce the power consumption dramatically, you might increase the response time. So those are issues that are not exclusive. Another frequent metric is the throughput. Throughput is the number of transactions per second. For example, that the database center can support how many queries per second is the backend able to support. So those are metrics that come from your understanding of the system and what users expect from the system. We will see in one of the chapters of the course that defining a metric can be done relatively easily once we understand the system, but we need to be careful about one little aspect, which is the operational conditions under which the metric is measured. This is called the viewpoint. So we will see an entire chapter on this. Depending on how you measure and define it, you may have metrics that make sense or that are misleading. So it will be important to understand those to give the correct operational viewpoint. So we'll talk about this in detail later. Right now, let's remember we need to define metric well. For example, here in this performance evaluation of an operating system, the metrics were taken as the ones that are highlighted here: number of CPU cycles, number of instruction, etc. In the other example related to power consumption, not surprisingly, the metric is the total power consumed in average over time. But sometimes metrics give us surprises or difficulties. For example, here is the result of the performance evaluation of a web server that is submitted to the load of a standard workbench. So we measured the response time to the request, the throughput, how many transactions per second the web server is able to satisfy, and the power consumption here. And I have 5 different configurations that I call A, B, C, D, E. Which one do you think is the best? So we will try now to do a Zoom poll. So I would like to Hossein to start the Zoom poll if you can. Thank you, Hossein. Okay, I realize I closed the poll and perhaps the setting was not as it should have been because we were sharing it. Okay, so anyhow, let us now see the results. The majority says D, configuration D, but the correct answer is not this one, because in reality, what happens here, well, we have a multidimensional metric. We have response time, throughput, and power consumption. And we see that none of the metrics is really better than the other. Here I'm plotting what is called sometimes a spider plot or a caveat diagram. I'm plotting on 3 axes, the metric, and here I'm using minus power consumption and minus response time, so that large means good. So a larger value on the power consumption axis means it is less power consumption. So a configuration that would be optimal is one that would be on the top everywhere. There is none. So that's the first take-home message here. When we do a performance evaluation, you should not expect that there will be one metric that you can measure and you can rank everything. This is done sometimes you must do it for whatever reason. This is done by consumer organization that compare the performance of whatever washing powder or things like this. They aggregate a number of different metrics together by giving weights, but this is not very exciting. This is largely misleading because you cannot compare response time and power consumption, right? Those are contradictory and different things. So the first thing to remember is, well, you'll have to live with complexity. You'll have to live with multi-dimensional metrics. Right? Don't try to aggregate everything before ahead of time, because that might be very misleading. However, there are still things we can say. When we have a multi-dimensional metric, in general, we don't expect, with rare exceptions, we don't expect one metric to be much better than one configuration to be much better than all other ones. But there can be configurations that are non-dominated. Here it's A and D. Non-dominated means that there is no other metric that is better in all dimensions. For example, configuration B is dominated by A. So B is a configuration that is not interesting. So we can distill the result of our performance evaluation here by saying there are two configurations of interest. Configuration A, that is better from the viewpoint of power consumption, and configuration D, which is better from the viewpoint of response time and throughput. So the first concept here to remember is non-dominated, is the correct comparison to do when we have multidimensional method. Metric is, of course, the first thing you need to define. If we look carefully at what those papers have done, we see immediately that there is another aspect that comes. It's the load. In order to measure a performance, you need to define what you measure, the metric, and the conditions in which you measure. The conditions have many, many different aspects. One very important one is the context of computer systems, is the load here. Here, the load for a computer system can be a benchmark. A benchmark means a program that is meant to reproduce typical conditions. Of course, it's very subjective, but in many fields, there are popular benchmarks that can be used for doing fair comparisons. Here, the load is captured here in those fractions of time, which is assuming that, for example, which is specifying the percentage of time when we use the, which is capturing the different fractions of capacity used by this equipment, full, 50%, or zero here. So this is another way of defining the load here. Last, if I compare those two examples of performance evaluation, the first one was not so much interested in finding absolute values. It's a comparison. So if you do a comparison, performance evaluation is easier because you're not trying to find absolute value. The second one is a different nature. It's called an engineering rule. The second one is trying to capture, via some approximate formula, the performance of a system here. So engineering rule, comparison, those are very frequent goals that we find. In general, of course, what we will need to remember is to be able to specify our goals well. So this will be one of the exercises that you will need to go through when you define your mini project. What exactly is your goal? You cannot evaluate everything. So you have to really think what is important for you. So that will be your homework for the coming weeks in the background. Voilà. So I've started with a very general and superficial pieces of advice about how to do performance evaluation. Of course, if you come to this course, it is to have more technical things. But again, I think this part one of the methodology is very important and explains many of the difficulties we have in doing projects. So if you remember those first few points, that might save you time. Now let's go through patterns things that happen typically when we do a performance evaluation, and that it's better to know ahead of time to avoid doing mistakes. The major topic that causes a lot of problem when doing a performance evaluation is factors. So factors is anything that influences the performance. Here's an example that was measured a few years ago on a self-organized mobile system projects in the framework of the MIX research project of EPFL. Here we are plotting the speed of a mobile as a function of the throughput achieved by a mobile as a function of its speed. So we are using mobile sensors that are sending data, and in principle, the faster you go, the less good you expect the performance to be, because you're putting more randomness into the wireless channel. You may break the TCP connections. You may need to restore them. Even the physical channel may break and need to be restarted. So we expect in general TCP throughput to be negatively affected by mobility. But here is an example where we find the opposite. So there are other papers, notably by our colleague Matthias Großglauser, who became famous for one of his works on showing that the capacity of a wireless channel increases with mobility. So this is in some sense also not impossible, but this is what we found. We instrumented about 30 different mobiles, measured the throughput using iPerf, and this is what we found here. We see a number of points. Then we did what is perhaps a bit bold, a linear regression. We'll talk about that, and I'm sure many of you have already encountered this many times. And so the linear regression gives us a straight line, and we see that the slope is positive. Therefore, we can think that throughput increases with mobility. Factor is mobility. My metric is a TCP throughput, and this factor positively impacts my metric. What do you think? I'm asking you for a guess. What is your best guess? Can you conclude that yes, mobility increased throughput, or do you have another opinion? I will close the poll in a few seconds. I close the poll, and we can see the results. The majority says it is true, but perhaps only for a very specific system. Well, here, let's see the reality. The correct answer is no. That's the opposite. In order to see why, I'm showing the same diagram here. The diagram we saw is this one. But now I'm putting a label on the data points. The label is S or L. And this label corresponds to the socket buffer that was used in the setting of those mobile devices. For some reason, which is probably incidental, some of the devices could have a small socket buffer size and others a large one. They were using different operating systems and different versions, of the same operating system, and by default they were configured differently, and nobody really cared, because changing this size requires fiddling with configuration files that you don't want to do. So nobody really cared. But now if I do care and I label the points, this is what I found. I have a cloud of capital L points and a cloud of little s points. Now I can redo the same exercise of fitting a straight line, doing a linear regression, to those two clouds. And here's what I find. I find for the cloud of s points a line that is quasi-horizontal, but slightly decreasing. And for the L lines, a line that is clearly decreasing. So in other words, if I reveal the socket buffer size, I see that speed has a negative impact on the metric, the throughput. So the conclusion that we had is inverted here. So why were we fooled? Well, this is the pattern called of the hidden factor. There was a hidden factor that played a role in the performance, affected the metric importantly. So a factor in general is anything that affects the performance metric that we're measuring. And usually, when you measure something, there will always be the desired factors, the one you're interested in, for example, here, the speed of user, but also nuisance factor. Nuisance factors, there are factors that we would like that they don't exist, but they do exist. And the problem is if they start impacting the performance dramatically, like they do here. So what we measured in the previous slide was in fact more importantly affected by the size of the nuisance factor, which was the socket buffer size, more than the speed of user. So there was a confusion between those two factors. How can we avoid that? Well, the first thing is we need to be aware of all hidden factors that could be unhidden. So if there are factors that you can easily address, then you should address them and incorporate them in the analysis. For example, instead of doing a simple straight line linear regression, if we know that the socket buffer size is a factor of interest, you could do a linear regression with respect to not just the speed of the user, but also the socket buffer size. And then the factor in front of the speed of user will give you the number of interest. Very often, it's not always possible to be aware of all factors, but it's important to screen what are all the things that could impact in a way that would distort the metric. And distortion of the metric, as we will discuss in a few minutes, is captured by independence. This is well known in another context in statistics in general under the name of Simpson's paradox. So exactly the same paradox occurred here in the social sciences in a textbook case that happened in 1973. That's the UC Berkeley admission results. You have on the top the percentage of admitted men and women, and 44% of men are admitted, whereas 35% of women are admitted. Therefore, there is a legitimate question. I mean, is UC Berkeley, or at that time was UC Berkeley, have a negative gender bias? Right? And those figures tend to admit that, yes, there is. So this went to court, and then a smart lawyer looked at this table and found out the following thing, that if we observe a hidden factor, the hidden factor in this case is the department to which you apply. So here, the department, ABCD, so you can imagine some of it is the medical school, another one is engineering. You see that they have radically different percentage of admission. You see, for example, that department A has an acceptance rate, which is very large, and same for B, whereas the department C and D has a very low acceptance rate, right? Half of that for the former ones. And there is a correlation between where the gender and the department. Most women, we see here in the numbers, apply to the department C and D that are very selective. And if you look at the numbers per department, you see that there is no bias or no clear bias in one direction or the other. In fact, for 3 out of 4 departments, if there is a bias, it is more against men than against women. So this is another example. That's the historical example that every textbook in statistics will give you of exactly a hidden factor, also called Simpson's paradox here. So here again, the fact is that the metric, in that case, the probability of being accepted in a at the school was influenced by a hidden factor, and this hidden factor had a very important role. The hidden factor is the department to which you apply. It's not because you're a man that you're more likely to be accepted, but it is because you apply to a department such as engineering, where at least at this time there were fewer candidates than the other ones. We can do exactly the same thing for the TCP throughput example. If we, instead of measuring the slope of a linear regression, we can simply count how many mobiles had a large throughput. So this is just to make that fit in the framework of Simpson's paradox. And we will see that fast mobiles have a higher chance of being high throughput than slow mobile, 44% with 21%, from which we could conclude that fast mobiles have a higher throughput in general. So speed influences mobility positively. But if we reveal the hidden factor is we redo the same proportion for condition to being a mobile with a small socket buffer size or a large socket buffer size, we find that the probabilities of being larger than having a throughput larger than 1.5 megabit per second are inverted. They're exactly in the inverse direction. So that's another example of Simpson's inversion, Simpson's paradox. Why am I putting it in this form? Well, it is because in this form it's easy to understand how to avoid it. And this is our first formula of probability. I'm interested in conditional probability. I call a mobile good if its throughput is higher than 1.5 megabit per second. The probability that a mobile is good, given that it is slow, that is what I want to compare with the probability of being good, given that it is fast. Now, the law of total probabilities tell us that the probability of being good, given that it is slow, is the sum over all possible values of the nuisance factor, NF, of the conditional probability given that this hidden factor takes the value I, multiplied by the probability that this hidden factor takes the value I. So this is called sometimes the law of total probability. The probability of observing an event is the sum of the probability of observing the event and a special condition I. And the probability of observing an event and a special condition I is the product of the conditional probability of the event given the special condition multiplied by the probability of the special condition here. So this is the formula we have. And now we see that when there's Simpson's inversion, it is a typical case where each of these constituent probabilities here might be in a given order. The top is larger than the bottom here. But because we weight them with those quantities here, then the result might be different here, which is exactly what has happened here. And because the weights may be different in the two cases, given slow and given fast, we weight them differently. So of course, the result may be completely unpredictable here. There is not always Simpson's inversion, of course, but there can be when the weights are different. So how can we avoid this? Well, to make the weight equal. If the weight, the probability of given slow that the hidden factor takes a certain value is the same given fast, then the inversion will not take place because we will weight with the same weight here. So a first thing that's easy to see is that to avoid Simpson's paradox radically, one solution, if you can, is to make the weights equal. Now, the methodology question, what does it mean, in fact, to make the weights equal? So here I'm saying probability that NF is equal to I given slow. That means probability that the hidden factor takes the value I, given that some other factor, which is the speed, takes the value slow. That must be equal to the probability that the hidden factor takes the value I, given that the other value of the speed is fast. I propose some interpretation of this, and I would like to ask you, what do you think? Which interpretation, if any, is correct? I close the poll now. The majority says A and B, but the correct answer is A only. So that is a very important question because it's a methodological question. It is about the interpretation of independence. Two random variables are independent. Well, what is the textbook definition? Textbook definition of independence is this one. The probability of the AND of observing I for X and J for Y is the product of the probability. So product form is the textbook definition of independence. But it's also easy to see that the product form here means that the conditional probability, which is equal to the probability of the conjunction divided by the probability of J, will be equal to the probability that X is equal to I. So in fact, another equivalent definition of independence is whenever this conditioning is possible, which is whenever the probability that Y is equal to J is non-zero, whenever this conditional probability is defined, it should not depend on J, which is why this is called independence. So think about it. What does a conditional probability mean? If we think of probability in terms of frequency for things that are easily repeatable. So if I do an experiment 1 zillion times, the probability of finding A as a result can be estimated as the number of times I've seen A divided by 1 million. That's a simple but powerful interpretation of probability. And a conditional probability means out of, if I want the probability of seeing X equal I, given Y equal J, I will, out of the million experiments I have done, I will eliminate all those that do not have Y equal J. So I will keep only the results of the experience of the experiments that give Y equal J. Say there is only 1,000 of those. Then I will count how many times I see I out of all those experiments that produce Y equal J, and the proportion of those will be this conditional probability. So one way to think of conditional probability is we put ourselves in a constrained world where we force the thing that we condition upon to be true. When we say probability of X equal I given Y equal J, that means we force ourselves to be in a world where Y is always equal to J, because the probability that Y equal J given that Y equal J is 1. So we look only at a snapshot of the world where the event Y equal J is true. And the first thing to remember here is that independence means that the conditional probabilities don't depend on the thing on which we condition, which is why it's called independence. So answer A is correct. The answer B means that the probability of the hidden factor, given that we are assuming that the mobile is slow, is the same for all values of the hidden factor. Well, this is usually called uniform. We say a random variable is uniform if it takes different outcomes with the same probability. But uniformity of the hidden factor does not mean independence. So avoiding Simpson's paradox can be done by making the weights equal, which is also saying ensure that the nuisance factor is independent of the desired factor. Now, independence in experimental setting typically means that it doesn't matter what the intended factor is with respect to the desired factor. So the occurrence of the two are not related. So it is now truly a causality interpretation that we do. For example, very often it's not possible, right? The nuisance factor, if it occurs, it may completely invalidate your performance analysis. So you have to try hard to look for possible hidden factors, and we'll talk about some in a few minutes, common ones. But if you can, very often you can know what the factors are, but they're not all controlled. Sometimes the desired factor is controlled and the hidden factor is not. Sometimes it's the other way around. For example, if the desired factor is not controlled because it's imposed by the experimental conditions, For example, if you observe mobiles that have a certain speed, so you just observe on the road the speed of things, so you don't control the speed of every vehicle, then that's a factor of interest, but not control. And the nuisance factor, it can be chosen freely, for example, by subsampling. You could decide to measure only a certain type of mobiles. Then if you do that, you should make sure that the two factors are independent, in particular that the nuisance factor is independent. For example, by choosing the nuisance factor uniformly, not uniformly, but at random, independent of the desired factor, right? So if you choose, for example, to measure something for a mobile of a certain type of, for example, only car rather than bicycles, then this is your desired factor. The nuisance, the nuisance factor is the type of vehicle. The desired factor is the speed. Then, of course, the two are typically related, but you will have to make sure you pick a number of bicycles that are at roughly the same speed as a number of cars here. So the probability of choosing one factor for a slow mobile here was socket buffer size S for a slow mobile should be same as for a fast. And obviously it is because we did not have this distribution that we had this inversion. Voila, take home message here, identify hidden factors. For example, when you study the performance of an operating systems, well, there's a number of hidden factors. For example, if your computer is subscribing to Dropbox, and when you do the measurement, perhaps the Dropbox implementation is consuming a lot of bandwidth or power or CPU cycles, and perhaps the Dropbox program is not as good for Linux as it is for Windows, for example, because typically there are much more development money put on Windows versions than on Linux. So perhaps the performance of this program influences the performance of your measurement. And it's not that Windows would be better than Linux. It is simply that this specific program is better here. So those authors, for example, tried to eliminate all externus factor by reducing background activity and network activity. So one radical measure is to make them disappear. Another measure is to make them appear explicitly in the analysis by evaluating them and their impact. Or if you can't, or if you don't want to do that, is to neutralize them by randomizing them, as we have said before, making them independent. So we have seen the importance of factors, and of course you will need to define your metric, know your goals, and find some way of specifying your loads. Now, when doing that, let's talk about the scientific method. Here's an example. This is pre-COVID example when museums were open. Joe runs a museum and has a wireless shop to sell content that is used by people when visiting the museum. So visitors have to come, connect to a Wi-Fi kiosk, and download some paying content. Joe did a performance evaluation of a prototype of his information systems and plotted on the x-axis the offered load in transactions per second. A transaction is typically one visitor or is proportional to the number of visitors. The visitor typically does a fixed number of transactions. So on the x-axis is the number of transactions, and on the y-axis is the throughput as measured at the socket level, time it takes to download the content. The content in this case is small videos and audio files here. And we see that it starts to increase, not surprisingly, but here there seems to be a problem, a congestion problem, that when the offered load increases, the throughput decreases, so like the system is congested and cannot do its work. This is what Joe does as part of perhaps his mini project, right? Now, if you've seen that, what do you conclude from this? What do you recommend to Joe? Joe has access points, has Wi-Fi access points, and has a backend with servers that provide the content. And you could suggest to buy more access points, by a faster server, do things offline by calling Infomaniac, or it's impossible to do anything. So let's see what you recommended to Joe. I close the poll in 1 second. And we have a tie between buying more access points and changing your server. Well, what's the correct answer? Well, I'm not sure what the correct answer is, but Joe bought more access points. So Joe thought that the problem is in the access points. So Joe bought more access points, deployed another access point, and here's the performance obtained after the access point. So there seems to be a slight improvement, at least for some values here, but of course there's also some randomness in what is done here. We will discuss how to capture the randomness. And it doesn't seem that the problem really goes away by buying more access points here. In fact, what we have done here, what you have done, is answer a question that I asked you, and the only correct answer to that would be, wait a second, I need more information, because we were jumping into a conclusion, which is we need more access points. This conclusion has a cost. I will buy more access points, whereas we were not yet posing a diagnostic. So where is exactly the thing that we did not do optimally here? Well, it is that what is a hypothesis suggested by a performance result was taken as a conclusion. Here's another example of a paper that did not do that at all. So here, the goal here was to compare two wireless access technologies, ABR and UBR, for providing high-speed network, not wireless, sorry, wired technologies for interconnecting networks. And we see, we test what the authors say. We test the hypothesis that UBR with adequate buffering results in better overall goodput. Goodput here means throughput for TCP traffic than ABR. So in some sense, this is something that comes perhaps from a previous set of measurements, but is taken as a hypothesis. Then it's only a hypothesis, means we need to test it. Testing it means designing experiments whose goal is to break the hypothesis. If we make an experiment where we try very hard to break the hypothesis, and if it doesn't break, well, in fact, that's the only way we have to do science today. So science doesn't mean we know for sure something. It just means we've taken every effort to try to say or find whether this thing is incorrect, and it never worked. Right? That's the only way on Earth we can be sure of something. So we're not 100% sure, but that's based on the best we can do. So here they shown this to be true in a wide selection of scenarios, and they identified reasons that might lead to the bad performance of the ABR technology, and they tested each of them. And this reveals what? Well, but only one of them is very important, or two of them, the extra delay due to ABRN systems and the overhead of whatever feature of ABR or the ARM cells here is done. What do I mean by this? Well, do not draw conclusions unless the experiment was designed to test the statement here. So when we did a measurement, we can interpret the measurement in zillions of ways. But those are only suggestions. For example, the measurement we did before suggested that the wireless network was congested, but there might have been other reasons for that. Could be the server that's congested. So in order to know that, we need to design experiments or simulations that will try to take as main statement this hypothesis. So is the wireless network congested? Well, in order to do that, we need to do measurements on the wireless network. Perhaps one way to do measurement is to add another access point. That's a radical way that costs hardware. Another way is to measure what can be measured as a symptom of this statement. If the wireless network is the bottleneck, then that is visible in the statistics that you can take at the Wi-Fi level. So you have to go into the Wi-Fi level, and for Wi-Fi, it would be here typically the percentage of collisions. If this percentage is very small, then probability it is not the bottleneck here. So another measurement, so that invalidates the first hypothesis. So I make a second hypothesis. What is the server that's saturated? How do I know that? Well, again, once I know what I'm looking for, I know what is my goal, I can define a metric. For example, measure some critical resources in the server. That can be memory, that can be CPU usage, GPU, whatever. There's a number of them. Here, the memory utilization was saturated. Therefore, the server is indeed saturated. So this is validated. I don't need to do more. I have reached a fixed point, and this fixed point is called exactly the scientific method. Scientific method means define hypotheses, design experiments around those hypotheses. The goal of the experiments is to try to break them and validate by running experiments and see whether they say yes or no. If they say no, the hypothesis is incorrect, you have to define another hypothesis until you find a hypothesis such that all the experiments you can think of to invalidate it fail here. So if the validation is okay, you've reached a fixed point and you can start believing in this hypothesis. That seems a bit complicated and overly sophisticated, but it's really important. That's what I've seen in my past experience, and what other people say from other fields also is one of the critical errors that are done in statistical interpretation of experiments is that one. You interpret something as posing a hypothesis that is consistent with what you see, but is perhaps not the only one. And also this hypothesis has not been validated by trying all the consistency checks you can make about it. This is what we should ideally all strive to do when we do scientific results. This is why we need to do also things that are limited in scope if you want to be able to make statements that are true and not just pure hypotheses. In this case here, we see that after doubling the server memory, we obtain continued close to linear throughput, which indicates that this was indeed the right diagnostic. Voilà, so that is a very important part that you will be able to test in homework 1. In homework 1, we will ask you to go to a server that we have put in place that does the experiment for you. In the other homework, you will do the experiments, but in homework 1, we want you to focus on the processing, post-processing of the experimental results. So we have made a simulator that provides results, but you're free to design the experiment as you want through the interface of the server. And then we ask you to go to the server as many times as you want and answer a number of questions. So you can design the experiments, you can pose the hypothesis, and you will be able to do that. The hope is that by being trained to do that at the very beginning of the course, that's a reflex that you will use for the rest of the course and perhaps of your life. So scientific method is really the most important things perhaps to remember today. But there is another thing that is important in every domain of activity. There are usually what is called patterns. So patterns are things that repeat themselves that you find perhaps with small different details in different situations, but that tend to repeat themselves or being very frequently found. So if we want to save time, instead of exploring everything, we can first ask ourselves whether such patterns are occurring. So we should search for them. Very frequently we will find them, and they will save us a lot of time. The most frequent pattern in everything that we're doing in this field is bottlenecks. Here's an example that will explain what can happen when you're not aware of bottlenecks. So those guys who did this analysis here were asked to evaluate the performance of two compiler options. So they compile the big systems with option A and with option B. And then we did experiments on the performance here by measuring the time to complete a complex transaction. So the time is here in milliseconds. And for configuration A, with a compiler option, set of compiler options A, this is the time we find, and same for B. And we did it by having remote users that are accessing the system remotely, and local users that are accessing them via the intranet here. And we find those different numbers. And the expert, in that case, concluded that the performance for remote users is independent of the choice of whatever compiler options. And therefore, since most users are remote, it's only the debuggers and the developers that are local, it doesn't matter. Well, a criticism that we could do of this analysis, well, in fact, there was a bottleneck here. The fact that the performance is very different here shows that the remote access costs a lot. So this is number of transactions, it's not the time. It's not the ping value, it's the figure that is indicating the throughput here. No, sorry, this is the time to complete a complex transaction, sorry. So here, what this is indicating is that the bottleneck is really the access, the remote access to your system here. So what we're measuring when doing that, when we say it doesn't matter, is, of course, it doesn't matter because what we're measuring is the bottleneck. So the bottleneck is something that limits your performance more than anything else. That's a hidden factor if you're not aware of it. So here there's a hidden factor that is more important than the factor of interest. Of course, not surprisingly, we conclude that the factor of interest does not play a role. So we can sell A as well as B. But in reality, this is plain wrong. The conclusion should be, well, if we care about remote users, we should fix perhaps this large increase in response time due to the remote access. Perhaps there is a front-end server that is a bottleneck. Perhaps remote users access via a VPN server that is also very low performance, but that is the only conclusion we do here. So what we're measuring here is the bottleneck. So that's an example where the bottleneck is our enemy. We were trying to measure something and there was a bottleneck, and this, in reality, what we were measuring was the bottleneck. But sometimes the bottleneck can be a friend. For example, here, I'm trying to optimize a transaction system, and I instrument it to show the transaction costs in average. So I bombard it with 1 zillion transactions, and I compute what was the CPU cost per transaction, the number of disk access, and the network activity. So this is a compute intensive application. 1 million CPU transactions per instructions per transactions, 100 disk accesses, and 4 packets sent of the network. The capacity of the processor is 1 giga instruction per second. The disk can support 10,000 accesses per second, and the network can support 10,000 packets per second. We would like to understand we'd like to do an engineering rule to say how many transactions per second the system can support. What engineering rule would you do? How would you proceed in order to find such an engineering rule? Do a queuing theory analysis. We will do a module on queuing theory where we will learn everything we need to know in a short time on queuing theory. Do a simulation or do something else. What do you think? I will close the poll in a few seconds. Closing. And the majority says do a simulation, which certainly is better than doing a deployment. A small minority says doing a queuing analysis, but probably I would do something else. I would do what is called the bottleneck analysis. That's a topic we will see in detail in the queuing theory framework, but the essence is very easy to understand. Here, The trick is to compute the utilization of resources. Something is a bottleneck if it's used at its full capacity by the system. So in order to know how many transactions I can support, let me see how much of the resources, or the different dimensions of the resources, every transaction is using. There are that many CPU instructions per transaction, and the CPU can handle 10 to the power 9 instructions per second. Therefore, one transaction uses 0.12% of the CPU. Same calculation for the other resources. Here, the other resources are disk and network. One transaction uses 1% of the disk and 0.04% of the network. Therefore, what is the bottleneck for this system and for this type of instruction? It's the disk. Right? My disk is slow compared to what I want to do. Therefore, the capacity is, as a first order and very rough computation, can be obtained by the cost in utilization of one transaction per second, over this cost. That will give me 99 transactions per second. If I do 99 transactions per second, I will use 100% of the disk. I cannot go beyond. Probably I cannot go to 99, because if I'm here, everything is saturated and I might have bad behavior, but close to that is probably reachable, which means that the CPU will not be fully utilized. It will be used at 10% capacity and the network at less than 1% capacity when we are here. So the bottleneck is the disk, which means that if I want to analyze this system, I can simply give that figure by analyzing the relation of the transaction system with the disk. If I want to optimize it, the first thing to do would be to optimize the disk. And there is no point in this case analyzing in detail how queuing and scheduling of the CPU, or what are the collisions in Wi-Fi, this is using Wi-Fi, are occurring here, because they are at low numbers here. So the bottleneck is typically the only thing you need to model in detail. In queuing theory chapter, we will see a systematic application that will go beyond this. We will do more dimensions of such analysis to do a quick and fairly accurate queuing system analysis that can be done without simulation and without complicated models. So that's the first take-home message. Bottlenecks are your friend, because they simplify radically the analysis. If you know a system is heterogeneous and has a single bottleneck, you can ignore all the rest in the analysis. But of course, if you don't look for bottlenecks, you may make gross errors. You may spend a lot of time simulating, analyzing, measuring things that don't care, because there's something else that is more important. This is well known in the deployment of websites. When you deploy a website, there are many, many things that can become your bottleneck. There is the scripting time on the client side. There is the backend time. There is a number of things, and papers like this one have analyzed all the possible components. And the ideal performance optimization is when there is no single bottlenecks, where all the resources are at the same level. If we take the example of the transaction system in the previous slide, if we improve the disk by a factor of 10, then CPU and disk are at the same level. So now our system is optimally utilized in terms of resources. Wow, that was our first pattern, bottleneck, which essentially amounts in saying, well, many systems are not as complicated as you may think. It's only highly engineered and optimized systems that will have multiple bottlenecks where everything matters. Most systems, if they are just deployed without any particular optimization, they will have a bottleneck somewhere, and that's the thing to look after. Another pattern that is very frequently found will look familiar to some of those who took a networking course. I will illustrate on this figure here. Here I'm showing a hypothetical ring network, where at every node of the ring, there is one source that sends traffic. And I say it is UDP traffic. UDP traffic means there is no congestion control, means the sources send as much as they can. And of course, the links have some capacity here. And I assume this is completely symmetric by rotational symmetry. At every node, there is the same thing. I'm showing only one because the drawing would be clumsy, but at every node, imagine there's one. So at this link, for example, there is the traffic coming from the source, but there's also the traffic coming from the previous node here. So the two are competing. And if the source are sending at a rate that is larger than the capacity of the network, at the point where they merge, there will be packet losses. And UDP means we simply drop the packets, the sources don't react to that. Of course, if you're sending audio, like we're doing now over Zoom, and UDP, some of the packets are lost here, you hope there is an error correction mechanism, but that's another story. It's easy to do, and it's done in the lecture notes, to compute what I call the throughput. So the throughput is how much gets out of this exercise. So the source sends some amount of traffic, source I sends lambda I packets per second. This has to compete here on the first link with transit traffic from another source. So lambda prime I might be less than lambda I. This will occur if the source rates are very large. So there will be losses. So what goes here through will be less. At the next hop, they will be the same, because now this source is becoming a transit and it competes with a fresh source. So it will lose again some of it if the intensity of traffic is very large. So we'll have lambda I second, and what goes out here, I'm assuming the access links are very large capacity. What goes out here is lambda I second. Here in the lecture notes, we give an exact formula, but here I'm just plotting simply the numerical value, assuming, for example, the capacity of the links are 20 megabit per second, if you want here, as a function of the offered load. So this is rotationally symmetric, so all sources are the same. Lambda is the offered rate sent by one source. If all sources send below 10 megabit per second, since every source is using two links, on every link, there are two sources. So if every source is sending less than 10 megabit per second, then we are below capacity. So if we are exactly at 20, perhaps there will be also some queuing losses that might occur. But if we are below 20, there will be no loss. And this is this curve that is given here. Here there is no loss, which means all the traffic that's injected into the network goes out of the network. And therefore, we have this straight line here for the throughput here, which is the performance of my global network. But what we see is that if the traffic, the offer traffic increases, we have this blue line that decreases here. We can find an explicit formula for that, and this explicit formula will tell us that as lambda goes to infinity, this blue line goes to zero, like 1 over square root of lambda. So we have this paradox, apparent paradox, that if we put more into this network, then there is less that goes out. Why is that happening? Well, in this case here, this is due to the non-coordinated losses. When my source sends traffic at a rate, say, of 40 megabits per second, then it is competing with another source here. This other source will force me to drop a large fraction of my traffic. So my traffic is dropped, but at the next node, I'm also competing with another source, and both of us will suffer some losses. So at the first hop, I am injected into the network some volume of traffic that will not survive. It will be killed at the next node, but still, it will not survive, but it will force some of the other packets of being killed here. So I'm using some capacity on this link for some traffic that is of no utility. It is of no use to the final user. So I'm injecting work into the system that will never complete. Therefore, I'm using some of the resources of the system at a loss. And this is translated by the fact that the total utility of the network is decreasing when the injected traffic into the network increases here. This is called congestion collapse. Of course, this is known in the internet since the mid-80s. This happened in the internet, and we do what is called congestion control. So instead of using UDP sources, we use TCP sources. And with TCP, the source here will sense things and will know that it is not a good idea to send more than 10 megabit per second. So every source will, in a very indirect way, taste the water and not send more than 10 megabit per second. So we will stay at this level here. If the offered load is larger, the sources will not be able to send, so that the total throughput will remain the network capacity. So an ideal system is the dotted line. This system has a capacity, it cannot do more than 10 per sources. It will never do more. But if you engineer it well, it will do exactly that. If you do not engineer it well, it will collapse. So congestion collapse is the symptom that is as follows: the offered load increases and the work done decreases. It seems paradoxical, but it is not. We're all familiar with the road system. Whenever on a highway system, like the roads that are around the city of Lausanne, if there is too much traffic, there are huge traffic jams. What happens in a huge traffic jam, the capacity of a road segment, can be measured by the number of cars that can pass a certain line per second or per hour. It's around 10,000 cars per hour for a highway, for example, a 2 or 3 lane highway. When there's a traffic jam, the cars are forced to slow down, and then this capacity reduces dramatically. So this is an example where the cost per job, the job is carrying a car 1 meter ahead on the road, the cost, in the sense of how much time it takes to do that, increases with the load. When there is too many cars, the cars have to slow down, and because they slow down, the throughput of the road system decreases here. So that is an example of congestion collapse. Quasi all complex systems, in fact, all complex systems that I've seen are susceptible to congestion collapse. So if you build a complex system, it will have a capacity, cannot do more work than the resources that you've put. When it will reach its capacity, unless you've worked on mechanisms to prevent congestion collapse, it's very likely that it will go in congestion collapse. I've given an example of in a network where the problem was that we lost some packets before they reached their destination, but those packets have consumed some resources on the way on links that were themselves congested. So that's an example where jobs leave before completion. That occurs, for example, on call centers or on web servers. If people submit transactions, if the response time is very large, they abort the transaction. So that's called impatience. Jobs leave before completion, but of course, all those jobs have consumed resources on the systems that they're hitting. If the system is congested, the more congested it is, the more impatient the users become, and the more there is useless work being done. So that's another example. In general, there is also rejections of jobs before completion. That was the example I gave also in the network case, and that can occur in complex distributed systems, for example, where you submit a job to a processor. The processor needs to fork and send mini jobs that go to other processors, but the other processors are congested, so they will not do. So in practice, I mean, in theory, you do consensus and very complicated things, but in practice, you do timeouts. So the job that has forked the mini jobs will time out and will kill the transaction because it waited too long. But this timeout-based system is a recipient to create congestion collapse. So you must do something to avoid congestion collapse. We know what is done in networks. You rate control or window control the sources to avoid congestion. In database or web servers, you typically have what is called a gatekeeper or an admission control system, where you devote some of the resources on your compute net infrastructure just to analyze the requests that come, and you put a limit to the resources that can be used to that. So for example, you use 20%, the Apache web server, for example, has exactly that kind of thing. It uses a maximum percentage of the processor utilization to handle the requests that come into the server. If that percentage is reached, then it simply does not serve incoming connections, which means that they will be lost, but by being lost, they will not consume the rest of the resource here. Take-home message: as a performance analyst, you must think at least whether congestion collapse is possible. Perhaps it's not because your system was designed for that, but perhaps it is, and then you need to do something about it. Let's see another corollary of that. Here's another system. Now I'm using congestion control, so the sources use TCP. which we can see also as a way of doing fair scheduling, a way of sharing the resources of the network in a fair way. So roughly speaking, proportional to what you need. And here's how my network is. So at the beginning, my network was with the rates that are given here, 100 kilobit per second, 110, 100. There's one red flow and one blue flow. If we do things right, which is with congestion control, the blue flow will not send at 1000 kilobit per second because it has a bottleneck of 10 kilobit per second at destination. So it will send at 10 kilobit per second. And because it sends at 10, the red flow is able to send at 100 and there's no problem. Right? So this is the behavior when we do congestion control. Now assume we increase the capacity of this link here, which was the bottleneck for source 2. We multiply its capacity by 10. What will happen to source 1, to the red source here? I close the poll in a few seconds. Closing. And the majority says its rate decreases, which is very probably what will happen. So before, the situation was what I described a minute ago. After, when we increase the rate here, then the bottleneck becomes the link in the middle here, which if TCP is really fair, if they have the same version of TCP and the same round trip times, then this will be shared equally between the two sources. So each of those will get 55 kilobit per second, which is the fair thing to do if you forget the previous situation. But now if you're the viewpoint of source 1, you see that we've improved the network, but that has made things worse for source 1. So that is another pattern, which is called competition side effect, which is that in many complex systems, there is a resource allocation algorithm that is working implicitly or explicitly, because complex systems typically need to manage their resources. So there is some scheduling that does some arbitration between users. For example, by TCP, for example, by the gatekeeper that I mentioned. But there are also load balancers that will try to dispatch the users between all the available servers. So if there's more users, you will get less. But if things are a bit heterogeneous, putting more resources changes the outcome of the scheduling. It changes the equilibrium of the previous competition. And there can be an apparent paradox. You can put more resources and some may get less. So that's something that's often forgotten when we evaluate complex systems, so something to keep in mind. We can even go beyond. There can be even competition side effects that have the effect that increasing resources may make things worse for everyone. Here's another example. Assuming here I'm not using congestion control, so I'm back to the previous case, and assume the capacity of the link here is a variable of the first link here. So if the capacity here is 10 kilobit per second, because there is another 10 kilobit per second here we have a balanced case where we have two bottlenecks for the blue flow, and the first bottleneck is at the source. So the source will send 10, and the other red source will be able to send at 100. But what happens if we increase the capacity of this bottleneck here? Well, we see that here, we see that if I increase the capacity of the bottleneck here, then I increase the rate of the blue source, and we know there will be, this network is UDP, is not congestion control, so there will be more and more losses. As the blue rate increases, the red rate decreases, and there is congestion collapse. The total throughput, which is plotted here in blue, decreases here. So the rate of the red user will decrease. The rate of the blue user will stay the same because it will be able to send a bit more, but it will drop a lot. And at the end, the useful part will only get 10. So the blue user will get the same rate, but the loss ratio of the blue user will increase. So the practical performance seen by the blue user, he will get 10 kilobits per second, but with a large fraction of losses. So the application will be busy repairing and masking the losses, so the performance will be less good. So the take-home message here is, if we start with a situation at 10, and if we increase the resources, things get worse for everybody. So that's a case where investing more resources is bad, in fact, doesn't solve anything here. So this is an example of what I call latent congestion collapse. A latent congestion collapse is a system that's susceptible to congestion collapse, but by accident, you never saw the congestion collapse because there was a bottleneck. For example, the low-speed access for source 2. This network could not get into congestion collapse because it was bottlenecked somewhere else. This happens with a road traffic. When you build a new highway, at the beginning, people don't have enough cars to use it, or there's not enough parking lots in the city to attract people. So the system is fine because there is another bottleneck somewhere. If you remove this bottleneck, for example, if you build more parking facilities in the city, you might reveal a latent congestion collapse here. So that's an example where adding resources reveals congestion collapse, which appears paradoxical. Putting more does cost a lot usually, but is not necessarily a good idea. Voila, those are the patterns that are very frequent in complex systems: bottlenecks, congestion collapse, competition side effects, latent congestion collapse. And perhaps in some of the systems you may use, you might find some of them. Voila, that's the end of this lecture. We're a bit early today, but I think that's enough for the first lecture. Now it's your turn to put that in practice in two forms. We would like to encourage you to take quiz 1. Next week, there will be another quiz, which you must also do next week. But for this week, quiz 1, as I said, you can take the quiz as many times as you wish. On Moodle, when you submit an attempt, you will obtain feedback about your responses. And then you have an option. If you're happy, you can stop and move on to something else, like work for another course, take a break, or start homework 1. Or if you're not happy because you don't have 70%, or if you're greedy, you have more than 70%, but you want even more, then you can try again. And you can try again as many times as you want. If you're stuck somewhere and trying again does not improve your score, you simply should wait a bit. When you do submit a response, a complete quiz, what is called a review. Review means look again at the results of your quiz. If you wait for 2 minutes after submitting the quiz, you will get the answer to the quiz, and then you may try again if you're really desperate in this way. After you've done the quiz, then it's a good idea to start the homework, and you will have all the details on Moodle. Voila, that's all for the lecture today. Tomorrow, we will start a lecture on more technical topic, how to compute confidence intervals. That will be the topic of this and of the lecture tomorrow and next week. How it continues now. So now it's up to you. Of course, the quiz and the labs can be done wherever you want and whenever you want. But we are now here, we stay on the Zoom session until the end of the next slot. That means until 4 o'clock. And if you have questions, you can contact us via the chat. And if needed, we'll talk to you in a private breakout room about any questions you may have about the quiz or about the lab. Voila, enjoy and see you later.